Lisa, could you enlighten us about what righteous boredom means?
There's two kinds of boredom. Boredom because you've stopped paying attention and you've given up. And then there's righteous boredom, like where you're like, I get it, let's move along here. That's righteous.
So we want the righteous boredom. How many of you are righteously bored? It's okay. I won't take it personally. Is it good to keep going over this repetitively, trying to just reinforce it? Okay, good. It's I want you to learn this. I know that sounds silly. I don't want to just shove a bunch of material in the class and be like, yeah, it's just right there. No, I want to be your partner in learning this even more, right? That's my job. How many of you think you're going to use Bayes in what you do in the future? Many of you. Maybe your dissertation? Your second dissertation?
We're way past second.
That's right. Oh, right. That's not a good joke. Okay, so we left off where we talked about each of the choices of the parameters for the priors. The next part is where we load up all the parameters into JAGs. And I set a random number seed. And that stuff I'm just going to scoot over. But then we're going to talk about the JAGs model itself. And I wanted to get into, just again, what is the model for the data here? Because that's one of the important parts to it. And I want to say that because over on my previous notes, I just wrote out the expectation of y in my terrible handwriting. I'm going to try to write better, right? But in this step, in this expectation I put right here, I said that the f is a random variable, right? Right? That's the key difference between what I just wrote out to try to go and get you the expected value of the item mean from the step that JAGs or the Bayesian algorithm does. In the Bayesian algorithm, f is not a random variable. F is fixed at this step in the chain. All right, so we're saying conditional on a value of f. Once we condition on it, forget that random stuff. It's f. We know it, right? Even if we don't know it, we pretend like we do. Okay? So when we think about that, how this expectation changes leads to part of the model that we're talking about. Right? So when we do that, we still have our model. Y is given by that model equation. We know that what are constants in, or what are the things that are fixed? The mu is a constant. Lambda is a constant. When we're conditional on f is a constant. Right? So now all these terms right here are constant. So the only thing that has a distribution is E, and that's where we get to know the distributional form of our data. Right? So E is normal. So we know that y, pi, has to follow a normal distribution. We know the end part. We don't know what goes in between. All right, so this is sort of how do we decipher what a model happens to be? Or where do we get the model statement, or the part that says the model data likelihood, the key to our model itself? So here, now we can do the same type of process. We could take the expected value of this line, of this model right here, and we'll come up with the mean for y. We could do the same process for the variance of this line and come up with the variance for y. Right? And so the algebra of expectations, if you haven't taken the math stat behind it, the variance is the expected value of a random variable minus its mean squared. Right? So there's a certain set of properties that happens with it. So let's do the expected value as if f, whoa, wrong one. That smoky charcoal. There we go. Let's imagine f is constant. Right? How does that change this expected value? Now, when we pass the expectation through the sum, the constants come out of the expectation, and what we're left with is the, mu, mu for the item plus lambda for the item f for the person, right? Plus the expected value of E, and we said before the mean of error is 0, so that goes away. So we know the expected value for the conditional distribution of y given f effectively. And in Bayes, we typically also say mu and lambda, all the other parameters that go with it. Mu, lambda, and psi, really. Well, we know the mean of this is now mu for the item plus lambda for the item times f for the person. Similarly, we could figure out the variance of this thing. I'm not going to draw out the entire algebra of expectations, but really what we want to say is this is the expected value of y minus the mean of y pi squared. Right? Well, there's some pretty quick shortcuts we can do with that. We know that if we add constants to a variance, it doesn't change the variance. We multiply the variance by a constant, it changes the variance by that constant. So it multiplies the variance, essentially, rescales the variance. So if we look at this, again, all this is a constant. What we're left with here is, actually, if we do the variance of y, say mu plus lambda f plus e, what we're left with, because everything else is a constant over here, these are all constants, is we're left with the variance of e. And the variance of e, we didn't really define it before, but variance of e, we said that e was normal by definition, actually normal, zero mean, variance of psi squared for the item. That's usually what we say. All right? We good with all that? So that means the variance is psi squared for the item. And that's our model. That's how we develop the model in the JAGS code. We're looking for the conditional model itself. And so this brings up an issue. You may have seen, and actually you saw me last week on the board make a mistake with this, but there's a more familiar form that you often see in factor analysis when you talk about models and so forth. Often what you say is the entire, like if you want to talk about the entirety, oftentimes we want to say, what is y? This is conditional. Right here. When we see factor analysis more frequently, and I'm going to do this with a vector now, a matrix now actually. So now this y is like a big matrix of data. What we often say with this is it's multivariate normal, which I'll still denote as normal, but just put matrices in to apply it. And oftentimes we say that the mean of that, when we allow the mean of the factor to be 0, is given by the vector of means. And the variance of this is the matrix of factor loadings times the factor variance times the matrix of factor loadings transpose plus size. All these are matrices right here, right? Like that. Right? So that's a conditional model. And that's the difference between the two approaches.
Marginal or conditional?
I'm sorry, this is marginal. Ah. Wrong time to make a mistake, Templin.
So if the factor goes before the comma, it's conditional. If the factor goes after the comma, it's marginal.
That's right. That's it. That's exactly right. It's really, this is not conditional on the factor. Technically, if we were doing Bayes here, we could make this conditional on mu and or the mu vector, the lambda matrix, the phi matrix, and the psi matrix, right? This is a big distinction, and it brings up an interesting modeling point I didn't bring up last time. We could actually do the analysis in either way in JAGS, conditional or marginal. Most of the time when you see this analysis done, it's conditional. The reason for that I'm going to guess is that JAGS code is really difficult for marginal. You can't, I tried to get an example of marginal actually when I was building the whole lecture before. And what I ran into was this matrix product threw me off. There's a section in JAGS manual, like chapter 9, that talks about matrix operations, and they sort of show different matrix products like in R, but it doesn't attach to text. And I could not find an example online where I use that matrix product. So that means I had to loop. If I want to do a matrix product, I have to loop through, like a double loop effectively. I could probably shortcut one of those outer loops and make it vectorized, but that thing would take a long time to implement in JAGS, since I forget it. Whereas this is much more direct. But it brings up an issue that shows up in a lot of different parts of statistics. Why is this okay in JAGS, whereas this is not okay, but it's not okay if we're going to go do like a joint maximum likelihood. We don't estimate F, right? Is that what you were going to ask?
Mm-hmm.
So it brings up an interesting consideration about estimation that we don't talk about a whole lot, but in a lot of latent variable models, if you think of the factors, each of the factors is a parameter, right? So that makes the latent variable models a little bit different from your regression analysis, right? You go back to regression, if this were just an observed variable, that means we have a set of parameters, and every time we add a person, the set of parameters doesn't change. When n goes to infinity, we sort of know what happened to those parameters. When we add an f for every person, that means every person we add, we now add another parameter. So if we were to go and find like a joint maximum likelihood, if we try to maximize the likelihood based on f and all the parameters, some crazy things happen, believe it or not. Have you heard of this before? The idea, there's a famous paper by Naiman and Scott. I don't know if you know of this, but it's like 1940s, late 40s, early 1950s, right? So this is sort of this. When you have this situation and you use a joint maximum likelihood estimator, right? The estimates that you get are not asymptotically consistent, meaning you get estimates that aren't guaranteed to converge to their true value in probability. Right? That's bad, right? But in Bayes we can. What? What's up with that? I have no idea. No. So the reality of it is, when you do this in Bayes, similar to what you do this with an EM algorithm, you plug in thetas, you get a little bit of a benefit from the optimization, because when each part of the algorithm, when you're doing theta, or sorry, when you're doing f conditional on all the other parameters, then you sort of know f, you get a feature of Markov chains that help allow them to have joint convergence and have that asymptotic consistency before. And I believe that the name is detailed balance, effectively, right? Each of these parameters is being able to be sampled, and the ones that you wouldn't know are conditional on ones you know, and so they effectively jointly converge in a way that allows it to be okay statistically. But that's one of the big differences between what you do here and what you do in another algorithm. That means if I had loaded up the parameters I'd asked for with the factor scores, right, and I reran my analysis, right here, that means I get all the f's as part of my analysis. Right? They're in there. I just allowed JAGs to tell me them. And there you have it. I have all these parameters in addition to it. To my, these are all the person parameters. And I didn't change anything in my syntax. So JAGs already has them there. All I did was have JAGs monitor them. I'll trace them, right? So this is a really big difference. If you do, if you think of factor analysis, Lisa made a comment last time about how factor analysis could be thought of as a multi-level model, right? If you're using multi-level model software like in SAS or LME, you don't automatically see all the random effects spit out. And if you're using like factor analysis software like in M+ or even Levon, and you go look at your table of output for your parameters, you don't see the factor scores. Right? And that's because their estimation is being done with the conditional model right here. I'm sorry, the marginal model. This is the estimation they do. There's no, you can express the likelihood without the factor in it.
So you don't need them.
You don't need them.
But you do need them up top.
Up top you do in the conditional model. So, why am I saying this? Well, I think if I'm going to code, if I code this, I would do either this model, if you did the Bayesian version of the marginal, I think it'd go much faster. The problem with me and JAGs, and maybe there's a way that I can get it into JAGs, I just haven't discovered the right help to find out how to do it with the matrix product. If I code this on the backside, or if I make a code, I could probably make a simple algorithm for you with the marginal, it'll go much faster. And the reason why it will go much faster is because we're avoiding 177 different steps to figure out parameters for, right? But marginal is not what you typically see in the examples for this. So that's sort of a big difference between what we're doing in Bayes versus what we're doing in not Bayes.
Do you end up at the same likelihood in both cases? Like, would you get to the same place?
You would get to the same parameters. Yes. The conditional likelihood is definitely not the marginal likelihood, unless the prior likelihoods are all uniform.
Well, if you can't figure out how to make JAGs do it, what hope do the rest of us?
Well, that's where I'm not a JAGs expert, but that's where I was just pointing out. There's quicker ways of doing this than in JAGs. Yeah,
I have a question about the marginal.
Yes.
Function. So my concern is whether the matrix operation will be positive defined.
So in this case, yes, you need to have this positive definite. The way that we structure this model, we're okay. It's the situations where why we're okay is that there's nothing that we can specify in here that's going to lead to indefiniteness without having, because phi is diagonal, or psi is diagonal. That's what the argument would be. Right? So what am I saying? In our model, our phi matrix is a 1. If we had more than one factor, this would be a covariance matrix. And what I didn't tell you is, if to do that, I haven't gotten to how we do that. It's an inverse Wishart. But that thing's going to be positive definite. So that means this term right here should be positive definite unless these are like 0, which would be never happen, right? And that's the case. The only way that it would be we'd run into positive definite issues is it's something when we add to it in the off diagonal that causes that to work. But we have zeros in the off diagonal for this model. So that means this whole thing is pretty much guaranteed to be positive definite for most choices of the priors that we have, subject to when you get really large numbers, you may have some stability issues with the computer. I think that's the argument I make. I don't know that I have proof for that claim. But.
I got a question, which is not directly related.
Oh, no problem. No problem at all. Yeah,
so in
good.
IRT, when we do it like in Bilog, it uses marginal likelihood. So basically what I understand, it integrates out the
That's
theta
right.
and then get ABC. But in realization in the computer, it's using conditional, like the EM algorithm is essentially conditional. So theoretically it's marginal, but when we realize it, it's conditional.
Yes.
So my question is like, how is it kind of in the middle of the ground?
Yes. Yeah, that's exactly right. So the EM algorithm in IRT represents sort of a condition. It gives you a marginal result, but it does so with a conditional. And there's some results that show how you move along with it. But it's sort of the same idea, because in the M step, you treat F as known, and because you have to iterate between E and M, you sort of get the same balance, the detailed balance that you would have in a Bayesian algorithm that would allow both of them to jointly converge.
So is it common, like in other algorithms, that even though eventually you get marginal results, but the way you realize it is still through conditional?
It could be common. That's one method. And actually in IRT, there's other methods as well. The difference would be in the marginal likelihood would be an integral right here. And so instead of having to do EM, every step of the chain, you would go and do an integral across values of theta. You'd have to integrate out theta from all of your likelihoods. You express the likelihood function itself, then becomes really difficult, because every step in the chain for each person, you have these quadrature points that you're integrating across to get. But you could actually build an algorithm with Newton-Raphson there with the integration, where you wouldn't have to actually do the EM algorithm. And for instance, if you look at M+, and you run a factor or an IRT model, and you're looking at, and if you're sort of watching the window, the black box, it tells you a little bit. There's a little 2-digit code that says EM in most steps, and then it flips over to something that's like QN, I think it is, quasi-Newton. That quasi-Newton step is where you're not doing The conditional, it basically flips to the marginal by using integration. So it tries to get away from where theta is. And they have a catch for it. Sometimes they call that an accelerated EM algorithm. There's certain EM gets really, really slow by close to convergence, so they try to do other things to speed it up. But there are other algorithms like that, or hybrids of Bayesian versus not. And I guess EM you could think of as a hybrid algorithm. And the Robbins-Monroe algorithm works in a similar way as well. So.
Do you invite a question? And if it's more than we want to get now, it's fine. But what is the part that you can figure how to do in charts? The matrix manipulation?
That one, matrix multiplication.
And this may be off, but it may have to do with how remember that we were talking the other day that in charts you can upload different ways of writing your syntax model.
Yes, yes. And
I think that if you go into writing it directly in matrix form, that may be the way to get there, but I'm not convinced.
Well, if you can find it, I would love it, because I would be able to show the marginal pretty quickly.
Let me send you what I have.
That'd be great. I would really appreciate that. I don't want to claim to be a JAG. I'm not a JAGS expert, so I'm not going to claim that. But here's the thing: I was like, I've read the manual. I actually read every page of the freaking manual, and that I did. And then if you look in so here, I load the bugs module, which is actually loaded by default in the RJAGs, right? And it's like vector or matrix value functions the bugs module. And so it says matrix multiplication, and it's got matrix transpose. And I can't get the conforming arguments to work. And I must have spent 5 hours trying to get this work. I kid you not. I was very grumpy. It was a Sunday.
I think I remember that.
Sorry, I was very grumpy. It won't narrow it down. but yeah, I think it's there. I don't know where it is. But if anyone knows where that is, let me know. Extra credit? I don't know. I'm going to give you, again, you have a chance to get all perfect scores. So it's not all that, extra credit isn't needed. But
Can I ask a quick question about words?
Yeah.
So marginal, I loved your question, by the way. It's a conditional way to get to marginal, and then we call it marginal maximum likelihood.
Because you can show that the result is what the marginal result would be.
But getting at it the conditional way.
Yes, that's right. We're conditioning our way to a marginal result. So here's the thing. If we have a non-marginal result, it's bad. Right? And so the cases where that's bad that I know of, there's probably lots of cases, but in early IRT, there's a program named Logist. I think it was made by Fred Lord, right? So pretty bright guy, but before, I think, Bach and Aitken, and before things really moved along in the 80s, they did joint maximum likelihood. So what that meant was that the likelihood function was now this huge dimensional problem, because now every person's theta was in it as well. That's bad.
Okay. Are there any other examples of bad non-marginal that I would see?
Anything else doesn't come to mind? Maybe anybody else know bad ways of doing things? There's a conditional maximum likelihood that shows up if you can get certain results. Like if you take the Roche model, or you take the one parameter, and you see that the sufficient statistic for ability is the sum score, then you can condition on it and make that work. Now that's okay too, because you've effectively gotten rid of, it's conditional, but you're not estimating the value of the ability parameter, right?
That's just to get the item parameter.
That's right. Here, the thing that I don't know, and I'd love to know more, how many of you have used win steps?
That's a Roche thing.
It is.
Yeah.
They use joint maximum likelihood. I say that because I was on a peer review panel for state assessments. Right, so every state tests their kids, part of the law. And some of the vendors out there, their technical manual and the review material, they're, we're using joint maximum likelihood. And I'm like, really? I think that's pretty bad. Nothing changed. No one wants to listen, but that's, when Steps does it, it must be okay. But,
can I ask you a silly question about
yeah.
this? The part that I'm trying to make sense in my little brain is conditional on what?
Yeah, actually they're both conditional. Right? So in a Bayes sense, they are both conditional.
Because that is what I was trying to get in my head around.
Right. So if you've got a multivariate normal is an easier way than looking at it here, because these are weird distributions usually. If you have 5 variables in a multivariate normal, right? You can let's say x1 through x5. You can create the conditional distribution of x1 given the rest. Right? You could also come up with the marginal distribution of x1, not given the rest. Right? Or you can come up with the marginal of any weird comparison of that. You can come up with the marginal distribution of x1 that's conditional on x2 but none of the rest. Right? There's lots of ways that you can make this work. What we're marginalizing across in the algorithm I'm talking about here is the additional parameters that are induced by having people or having observations. So that's the key. And so when you look at a marginalized result like in a Rmsea algorithm in multi-level, the likelihood itself is not expressed as a function of the person parameters. That's the key. Marginal across people or marginal across observation units. Yeah, very good. Thank you.
That helps.
No, it helps. I gave incomplete information. I apologize.
So what if my items have other observed variable predictors too, such that my mean, my intercept, is conditional on those in my marginal distribution?
Yes, that would be a case of this.
What the hell do you call that?
It's still marginal across the person parameters. If you marginalize the things that the units induce, so that you basically, when you're adding observations, there's not more and more parameters in the marginal likelihood, that's the thing.
So it's conditional with respect to the predictors because they're not part of your likelihood.
Right. Well, they are part of the likelihood. They'd be part of the mean there.
But they're not. They
You
don't have
mu plus
distribution.
beta x.
The situation in which they don't have distributional assumptions, like all
Right.
you're trying to. That's what I'm trying to get at. What do you call that combination?
Yeah, if they don't have, they'd be conditional upon. Yeah. It's a conditional mean then.
The conditional mean
Right.
through a marginal distribution.
It would be so it'd be a conditional likelihood. This likelihood would have marginal. It's conditional on all this and marginalized across the person. Is this getting way deep? No.
It's awesome.
I don't know. Let's see. So how are we doing? Does that help, Lisa?
Yeah, I'm trying to tie words to ideas and make sure I'm using the words correctly.
Mhm.
That's what I'm trying to do here.
This marginal conditional thing is a pain in the ass. I'll just say the word.
The way I think about it, if we had all these person parameters, we still have this conditional distribution. We've got these person parameters, and they're being annoying. So we're going to integrate over that, which removes them, but it's still conditional. So it's conditional, but we've integrated across the annoying parameter to get it out.
Yeah. So that if you look at marginal likelihood, if you broke it down to where y was with respect to person, right? Every person that you add has the same one, doesn't have additional parameters. That's the key. Every unit that you add doesn't add parameters to the marginal likelihood. We call it the marginal. It's marginal across the unit parameter, the personal parameter. I'm trying to, whatever the random variable is that's in there, the random effect, the latent variable, what have you.
So I guess it's the marginal conditional.
It is. There are always parts that are conditional, but what we're focusing on is the thing that screwed up our asymptotic consistency. It's marginal across. Blah. Is this bad? Nah.
How does that change if this is an IRT model and now we don't have, like, we were dealing with the Bernoulli conditional distribution?
It changes in that we don't have this nice form down here. The form of the algorithm or the likelihood that's not that is expressed actually has an integral in it. It's unresolved. There's no closed form to it. Right?
You have to do it the first way.
You could set JAGs up to have quadrature points in it if you wanted, and sum across each observation and come up with a marginal likelihood if you wanted to.
And lots of IRT programs do that. Get that integral we can't actually evaluate that interval, but we can approximate the interval with quadrature points.
That's right. Yeah, that's a good point. The numerics are never exact, but we try to get close enough with some precision, some level of tolerance and precision, I should say.
So when I say then in CFA, or anything where there's normal,
Mhm.
the random effects or wrong class factors
Yep.
and errors, then there is an exact answer in terms of the marginal.
Yeah.
But if it's not normal, or it's like Bernormal or Normuli.
Yeah, yeah, Normuli, I like that one.
Right, that was Lindsay Filey, she came up with that one. Then like the answer is approximated.
Yep.
Quadrature.
That's right.
Or some other method of getting close. but
That's
not-
right.
It's not gonna be exact.
That's right.
Because then you have to be like, how many quadrature points, and how do you decide, what if it's adaptive or not, or like
All sorts of crap that goes on with the approximation. Yes. And then so you could, and then in the algorithm that you're building in JAGS, you have to write the JAGS code to do that approximation.
Yeah, fuck that.
How do you really feel about it?
Other thoughts or questions? Are you righteously bored?
I have a question.
Yes.
The factor score.
Mm-hmm.
So based on the output
Mhm.
from R,
Mhm.
statistically they are very, very high.
Yeah. That's because we ran the unconverged, the non-converged, I ran the standardized factor model in that first one, where we had convergence issues.
Because the negative times the negative is a positive.
That is exactly it. And so what you're going to see, if I could, I don't know that I can extract the factor scores to show it, but let me see if I don't even know if I can, but if I were to plot this for one of the factors, you would see that the chains would be almost, if you look at the y-axis, there would be one at a positive value and an identical one at a negative value. And those, most likely the chains are in those two spots because of the way the algorithm assigned starting parameters and then had a kind of a jump to get started. It's usually just a start. This is a Gibbs sampler, so there's no updating, there's no rejection sampling. So let me do this though for the other one. This is, so we fixed the Gibbs sampler by saying we're going to do the marker item, and that's all it took to fix it. We had one item that was positive, which makes all of them have to be positive, because the mode for the likelihood or the marginal likelihood is when it is the reflection point. I think that's right. It's reflected, right? Where f is negative f, right? And so, or negative lambda times negative f. Well, if one of the lambdas is positive, you can't get to that reflection point. So did I use that right term? Reflection, is it reflected around 0? It's not the same 2 dimensions though. So
Yeah, right.
yeah, so it's
About the origin.
there you go. That's about the origin. Thank you.
But what if you didn't want to do the marker item? What if you still want your z-score to factor? Is there no way to do that to make it not have 2 modes?
There's 2 ways of doing it. Number one is to use the marker item and then after the chain, standardize. So go back and every iteration go and standardize all the loadings, right? The other option is to go and set really tight priors and starting values on the standardized solution. So make the prior strictly positive would do it for the loadings, or even one loading strictly positive would do it, right? In fact, I might be able to show that in just a moment. But here's the Ming-Chin. There's an example here with the. Oh, you know what? This is not the example. I need to save the X factor here. By the way, I put. If you notice when I'm outputting the factor scores, I put X in front of the word factor because JAGS will alphabetize everything. And when I want to see convergence, I typically want to see the item parameters first. If I don't do that, then the factors show up first, and it goes beyond where the R will want to output stuff, and so I put X there to put it at the end. So now I have to redo the initial values. But once this gets done, what you should see is the factors all have good convergence there. And anybody else want to talk about something? I have music we can play. Have some Markov chain music. So all of them are really nicely converged in this case. And Lisa, to go answer your question, let me try one thing. I'm going to go try and make the standardized solution converge with one trick. One small trick. It's like clickbait. This one trick will make your solution converge. I think this is it. I think if I do that, that allows it to be a truncated normal. But this is for all the lambdas. I think actually I can allow, if I do, well, anyway.
Is the syntax saying normal from 0
all to infinity, yep. I won't actually go do this because I don't want to overwrite my stuff, but I'll make it up for next week. How's that sound? Let's see if we can do it. I think all it will take is one being strictly positive. The rest can be whatever. It's like effectively saying I have a marker in direction. It's like a directive marker because again, it's only the mode is only in the case where it's negative lambda times negative f. This is the same result as lambda times f. Okay. So we ran everything. Now we're back up to where we were last time, but we've made progress, I hope. Are you getting a sense? Are you starting to feel like you get the hang of this a little bit more? Maybe? I don't know. All right. We ran the analysis. It converged. And you may be thinking, great. We're done. That took a long time. No. Convergence is the first step to nirvana. There's sort of multiple paths to enlightenment, right? Convergence, model fit, model result, right? Once you have all three, oh, I don't know.
That'll be very confusing to my Buddhist friends.
Convergence is the first step to the path to enlightenment. That's all I have to tell you. So what do we have to do to figure this out? Well, we're going to start now with the posterior predictive model check. Are we good on everything else, though? Questions? All right, now I'm starting. Officially starting. Posterior predictive model checks. We need to figure out if this analysis fit the data, right? And, you know, factor analysis was so awesome before. I mean, back in the day when we were using like M+ or Levon, I'd type summary, and it'd give me my parameters, and I could type, you know, fit dot measures equals true, and there'd be some numbers. Oh man, where'd those go? I don't see anything like that. All I have is output. And here's the bad part about it. When you're working with JAGs, because it's general, you've got to figure all that out on your own. You've got to create the model fit mechanism to make it work. And this is where I've never seen even dyed-in-the-wool Bayesians, like the capital B Bayesians, you know what I'm talking about? The people who have like the tattoo of Thomas Bayes on one shoulder and like Bayes.
Bayes is Bay.
Yeah, Bayes is Bay. Bayes theorem on the other shoulder. That's good. I like that. Right? Those people, I've never seen them flock to ML results ever before so much as in posterior predictive model check. So this is a part where I'm going to show you what's done and what's talked about in the book. And I'm going to be picking it apart because it makes me grumpy. Okay, so what is a posterior predictive model check? Do you remember this from the regression version of the class? It is where we take our converged chain, because convergence is the first step in the path to enlightenment. Nirvana. Maybe I should say enlightenment. A little bit more, I don't know. Never mind. Anyway, converged chain, we sample parameters or iterations from that chain. We'll take each iteration, and from that set of parameters from an iteration, we then pretend those are true, and using one of our model versions, we create data based on that. So we can create a brand new data set, and for each of those data sets that we've created, we make some type of summary statistic to come up with, to compare with what shows up in our data itself. Right? So the steps are, you need convergence, and then you have to come up with a way of generating data randomly from parts of the chain. Now, first question, why am I taking iterations of the posterior and not just taking values of the parameters from their separate posteriors? Let me give you some context first. I'll just show you this, and then I'll ask that question. So let's imagine I'm going to take 5,000 simulated data sets. I'm going to create 5,000 of these posterior data sets that are predicted. And so to do that, my posterior right here, my posterior distribution of, this is the part that I trimmed. It's a list, right? There's 4, each of the chains are saved in a different object. Or sorry, so I can't just go 1 through the number of columns in this thing. So this command right here, this do.call, forces me to take each list and just append, add the rows of each list on top of each other into a big matrix. That's what it's doing. So this is now giving me this posterior.all, and if we go and look at real quickly, see the dimensions of it. It says it's a large matrix, but so it took all of my, each chain had 2,000 or 1,000 post burn-in iterations. I put all 4,000 of those on top of each other. That's that first step. This code pretty much works for every type of example. So next, the hard part for me, and the part that makes this really hard to do in a general sense unless you're controlling the input and output. And by the way, at the end of this, there's a way, I'm going to show you a package that a friend of mine from grad school created called Blavon that does a lot of this easy for you, Bayesian Lavon.
Yeah.
You know that, there you go. It does this automatically, but I want to show you how to do it yourself because, I don't know, teach a person to fish and you fish for a lifetime, something like that, right? There, got it. Can't just give you the Blavon and say, here you go. Although my example with Blavon, same thing happened. First analysis, multiple modes, no convergence. Anyway, so again, what we have to do is take a look at the names of our data in this matrix, because we have to select which things are the lambdas, which things are the factor or the item intercepts, the mu's, which things are the unique variances. We don't necessarily need the factors as much, although we could use those. I'm actually going to switch to the marginal model to do this. But here we go. So all this is telling me, this grep function goes and says, which one of these column names has the word mu in it? And it says columns 13 through 22. That's right there, 13 through 22, right? So it's just a string, a character function. So I'm just going to load those up. And now I'm going to create a few matrices to save my summary statistics from each of the data sets I'm going to create. I could technically save all the data sets, but that's a little overkill for what we're going to do. It may not be overkill in every analysis, but for us it's going to be overkill. So I'm going to save the simulated correlation matrix. So from every data set we generate, we're going to save the correlations. Why is that? Because now after 5,000 of these iterations, I'm going to have for each correlation this predicted distribution of the correlation value from our chain, from data generated from our chain. And that's an easy thing we can compare with what the correlations happen to be in the data. That's the goal. I could do the same thing for the covariance matrix. And then there are some, because we're using CFA, there's some of the CFA fit statistics we could create as well. One of those being SMRMR. standardized root mean squared residual, which, kid you not, is calculated in 15 different ways. It all depends on the program. I learned that trying to do this. M+'s version, when you do this, would include the mean parameters as well. Then we could also create an Rmsea. Right? That's where it starts to make me interestingly angry, but I'll tell you about that why a little bit later. Okay. To do this, we sometimes may need the model-based covariances, and we also may need the model degrees of freedom. This is the number of free covariances minus the number of parameters in our model that are on the factor loadings or unique variances. And here I'm going and grabbing the data covariance. This is the covariance that's observed in the data. Hey, by the way, I just gave it the data. This is my covariance matrix from the data. What type of estimate is that? Well, that looks like an MLE, doesn't it? That's my problem with a lot of the Bayesian versions of this. Somehow, we have to do Bayesian things to our Bayes model, and then we're going to compare it to an MLE from our data. That just doesn't seem to jive with me very well. I don't know about you. We should be Bayes. We should read Bayes. We'll get there.
When it's convenient, I'm Argentinian. When it's convenient, I'm an Argentinian.
And this is why I'm a Californian always. It's always convenient.
I have an accent when it's convenient.
Ah, yes.
I can't find any time where it's not convenient to come an accent.
There you go. Although that'd be pretty awesome when you come in and you start speaking like, well, like me.
Or New York.
Oh, there you go.
Or Bostonian.
All right, so let's do this. First thing we need to do, we have 4,000 iterations in the chain. We're going to draw one at random and then use its parameters, right? This is different from drawing from each parameter separately. The reason for that is the parameters in their posterior distribution will be correlated. If you look at the chain, if we plot, here we could take a look. This is the model O1B posterior all. If I plot this, and I think it was 13, and this, and 14, of course. If I take a look at the correlation of it, it's 0.46. This is the correlation between the posterior distribution of the item intercept for item 1 and the item intercept for item 2. So that means if you draw them independently from each other, you're going to disregard this, and you're going to have a model fit statistic that doesn't fit what the model's telling you about the data. So the key in doing this is we have to draw the iteration, because the iteration locks them into the values that induce that correlation to begin with. So draw that iteration. We can grab the parameters and put them in matrices, mu, lambda, psi, and phi. And I'm going to use, just for simplicity, the marginal result that we saw before. I'm going to generate data with this multivariate normal right there, because it's a little bit easier. I could have done the data with the factors themselves, but I decided to skip that for right now. So here's my mean vector. The covariance matrix is lambda phi lambda transpose plus psi. So what is this telling us? The mu's for this iteration were right here. These are the values of mu, right there. The factor loadings are right there. Right, there's our marker. The factor variance is 0.62, and the residual variance is right there, the diagonal matrix. Right. So create the mean vector, create the covariance matrix. This is the covariance matrix for the marginal data. And then I can simulate the data. I'm using a multivariate normal, mean vector specified by mu, covariance matrix specified by the covariance. This is a marginal multivariate distribution, but it should be the same. And now we have a new data set. By the way, the sample size of this is the same sample size as we have in our data. It's important because part of the process of why aren't we just using the parameters themselves? The parameters may not reflect the sampling uncertainty that's in the data. So this is sort of a way to allow us to have likelihood, or these statistics reflect more data uncertainty for small samples like we have right here. Right? You can think of the sampling distribution of a multivariate normal with a mean vector and a covariance matrix with 177 observations. It's a 10-dimensional or 10 by 10 covariance matrix. The covariances are going to have some wiggle to them, right? That's what's going to happen. So we're trying to reflect that in our analysis itself. So there's our data. This is saving just the correlation. So the correlation of our simulated data is right here. There's our correlation matrix for this specific iteration simulated data. And this code over here takes the upper triangle. Whoa. There's the upper triangle put into a vector of that correlation matrix. So you can see that. And so then I'm loading it into a matrix with one row, so I can put that into my object that I created to save each of these correlations. So now I've saved every pair of variables correlation in one row of my aggregator here to go across. Then I can do the same thing with covariances. Although I got lazy, I didn't just take the upper triangle. So I need the diagonal, so I just saved them all. Actually, I did this because I want to compare this with the saturated model that I'm going to come up with later. So I just saved them all. To create the standardized root mean squared residual, I need to take the difference between what we observed in data for covariance, what we observed in our simulated covariance. But then we need to standardize it based on the data's value of the standard deviations. Right there. So this is the squared. It's right here. And so then this part does the squaring of it and doing it. So this version, this iteration standardized root mean squared residual is 0.146 for this sample data. And as SMRMR, we want to be less than 0.08, I think, according to Hu and Bentler, right? And we can do the same thing here with the Rmsea. Rmsea, I will note, depends on the discrepancy function to estimate the data. We don't have one. Yet another problem with doing this. Right? So an Rmsea, you can create an Rmsea for the ML estimates, which is what I have here. It will have a different scale than the Rmsea would have, like for the asymptotically distant free or distribution free estimator and so forth. Anyway, so to do this, I need the determinant of the data, the determinant of the simulated data, and then the trace of the data's covariance times the inverse of the other one, and reweighted and so forth. So this is Rmsea. So for this one simulated data set, our Rmsea was actually 0.1422, which is not good either. We want that to be less than 0.05, is that right? So everybody, questions on what I just did? I'm walking you through one iteration of it. Once again, what I do, draw an iteration at random, take the parameters, form the model matrices out of them. From the model matrices, I create the mean and covariance matrix for the marginal data and generate a data set. And then I take summaries. Covariance, correlation, standardized root mean squared residual, Rmsea. Shihan.
When we draw iteration, should we skip the burn-in?
Yes, it's always post-burn-in. Always in the converge section of the chain, otherwise these results will be very weird. But I'm going to run this the 5,000 times. I put a progress bar on there I need to actually run the code. Put a progress bar on there to actually show you how long it's taking. It doesn't take that long. So we need more music to play here.
Just to be clear, when you say you were taking an iteration, you were just sampling from our derived posterior distribution, correct?
That's right. So the object I created has all 4,000 posterior draws. Each chain had 1,000 posterior draws, and I lumped them into one big object with 4,000. So I'm drawing a number from 1 to 4,000 with replacement through each cycle of this, right? That's the goal with it.
When I think in discrepancy functions, yes, I think in the observe the model. How analogous your thinking with that will be here?
Okay, so that's the problem with the CFA SEM world. There's lots of discrepancy.
Yeah, absolutely.
So I think I would call the Rmsea that I talked about, where I said discrepancy function, that's the kind of the model fit function. Sort of you minimize the discrepancy under ML, and it shows up to be this function. And that function is this specific discrepancy right here is the difference. It sort of comes from ML result. In general, the discrepancy I'm more concerned about to assess local model fit. So I have a model implied covariance matrix, and I'm comparing it with my data covariance matrix, or actually the covariance matrix from the saturated model.
Yeah.
That discrepancy is useful, and actually we're going to do that as we go forward. So the difference between the two is that to create Rmsea, I have to use the kind of the log likelihood fitting function if we were looking at the ML algorithm. Whereas to do the standardized root mean squared residual, this thing right here, data cove minus sim cove, is the discrepancy you and I are thinking about normally. Yeah.
It seems almost simpler this way.
Yeah, for the data cove minus sim cove, yeah. And so we're going to use both to sort of evaluate the model fit. And it's kind of in a similar way in a CFA or SEM. You look at Rmsea for kind of a global picture of fit, but then you get into more normalized type of discrepancy, or some version of discrepancy for covariances themselves. Good question. Other questions?
So the only difference between what we would typically do in fit assessment is, rather than having one model predicted matrix to compare against the saturated model, we have 4,000 of them.
Yes, we have 5,000 of them actually.
5,000.
Yeah, and I'm sampling from the posterior, not taking each of the values of the posterior, because that process essentially allows me random draws. It's essentially an integral across the whole thing, but this is the sampling process allows me to take a smaller sample if I wanted to. This is actually a bigger sample. But.
And you wouldn't want to get an average of them.
The average of a
4,000 to reduce it to be one representing the 4,000.
No.
You know, you will get rid of the variability.
That's exactly it. Here, take a look at this. This is the, now I need the plot. This is going to be interesting to see if I can make this work. Dun, 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 dun. There it is. That is the histogram of the standardized root mean squared residual. So in a Bayesian analysis, you don't just get one number for the standardized root mean squared residual. You get this sort of certainty estimate of it. This thing is really interesting to me. Take a look at the sample. Look at the distribution of how long the tail is. We had one that was up here at 0.5. Right, the bulk of what we found was over here in between 0 and 1. That's a real interesting result, right?
It's not too surprising, right? Because your pole was way out in the ends of your posterior, and probably won't represent your data very well.
Exactly. Yeah. Here are the quantiles of the
It's a pretty cool way to think about these indices like this.
It is, yeah.
It's a deterministic threshold.
It's exactly right. Yes, it's much more. Now here's my certainty evaluated with it. Right? It's like, oh, okay. Well, for this, I would say that, I could go and compute the empirical percentile of where 0.05 is and say, the bulk of it. The bulk of this is under 0.08. Yeah, I guess the max was 0.46. The mean that we found here was not too bad either. It's 0.04. Let's take a look at Rmsea. Here's our histogram for it. That's crazy. Here's our density. That looks pretty symmetric almost. And then here are the quantiles. The lowest value is 0.13. The highest value is 0.22. So this tells a different story. It's pretty bad. And the mean value of Rmsea was 0.179. So each of these. So what do you think? If you were looking at this from the CFA standard of Rmsea, you'd say fit's pretty terrible, right? We could construct a CFI doing the same thing. We could construct a TLI. We could do all the model fit, pretty much all the model fit. But hold in your head though, model fit is using the MLE for one of the models we're comparing this to. Rmsea is comparing a saturated model with our model. And our saturated model is estimated by MLE, and our model is estimated by Bayes. That's my problem with this, right? Because I think we're actually reflecting too much certainty in our saturated model in this case.
And so, yeah, trying to compare the summary statistic to the threshold set by the MLE estimator is problematic.
Oh yeah, there's lots of problems with it. We don't know. We're not guaranteed this is going to behave the same at all.
Right.
So, so then the other thing we could do is take a look at those correlations. I know we're almost done for today, but the correlations that we had, we compiled all the correlations into this matrix, right? So we have 5,000 simulated data sets, correlation matrices. So I'm going to go and take all of those, and here's one of them. Here's the correlation between item 1 and item 2. This is the simulated values of that correlation, right? So the mean or the density, that's where our observed correlation happened to be, that red line for 1 and 2. Now again, observed correlation using MLE. By the way, did anyone ever tell you the Pearson product moment correlation is a biased estimator under ML? Did you know that? What? Why aren't we correcting that? Sorry. There is a correction. You could do that. But so my point is, if anyone ever asks you that, if you're ever taking comps or whatever, and they talk about variance or whatever, be like, yeah, what's the correction for correlation? Why does it not matter there? Anyway, long story short. What is this? This is saying, effectively, our model thinks the correlation should be systematically lower than our ML estimate, and again, that's important, thinks it should be.
That's misfit.
That is misfit, right? How do we tell? Well, we want to go and figure out the quantiles of this, and we could actually talk about like what is the percentile rank of our observed ML-based correlation. And so I have some syntax to do that. That loop right there. And with this loop of variables, so there's a function in R called ECDF, Empirical Cumulative Density Function, that could go and give us basically percentile ranks of our values. I'm going to go and highlight values that have percentiles that are above 0.975 or below 0.025. Nope, I guess I'm not. There they are, right here. So these are the values in the percentiles. You can see. So if it's above 0.975, then our observed correlation is bigger than kind of the average in our sample. If it's below, then our observed correlation is below what the average should be. And this is a list of the correlations that we flagged as being sort of outlying in the distribution. So this would be like an index of local fit. Right, so we saw that Rmsea result, and we thought, ooh, that's bad. Standardized root mean squared residual, oh, that's fine, but we lie with that a lot. It's here that this is telling us. I mean, look at this. We never generated the correlation bigger than the value in the data for some of these, right? We never generated a correlation smaller than the value for some of these. It's misfit, right? And so this now starts, this is how we start the discussion. This is the analog to what we think about with looking at local fit and CFA, and do we want to do model modification at all, which is another issue with generalizability, but so on our path to nirvana, we found convergence. Did we find model fit? No, I don't think so. So we're still not in nirvana yet. But maybe we'll get to nirvana by spring break. Spring break is nirvana.
No, my intuition wants me to say that if we do have good model fit, good model fit, our distributions for our model fit statistics would be lower and also maybe tighter.
Yeah. Maybe not tighter. When we get back next week, I'm going to show you the Bayes version. I don't see anywhere. This is the way I see people talking about it in books, like David Kaplan's book, and I haven't picked out the Song book yet, but the other books are Bayesian versions of SEM. I think there's a better way of doing this, where we could, instead of comparing it with the point estimate, you know, over here, we're comparing two distributions. And with two distributions, then what we can do is talk about kind of distributional overlap. There's all sorts of distributional tests, like a Kolmogorov-Smirnov, or although that's an ML, but you know, you can get divergence measures that you can talk about level of divergence, where 0 would be no divergence in the distribution. And I think we can use that to help indicate where model fit really needs to be. But I don't know. Still relying on ML for some of those as well, because once we generate the data, how do we summarize them in ML? So we can't get around it. Anyway, any other questions or thoughts? I hope I answered your question there. I don't know if I did. We went on a tangent.
That's good. Good.
Almost that time of the day for me. All right, everybody. Have a great afternoon. No homework. Homework 3 is out there, but don't do it yet. Okay? All right. Thank you. Have a great weekend. Do revise your other homework. And for those of you who didn't receive your homework graded yet, send me an email, please.
Still playing.
Right. Doing good.